Hello, I'm Myungju Kim, a PhD candidate at Seoul National University. Today, I will present my work entitled Foot-Stepping Algorithm of Humanoids with Double Support Time Adjustment based on Capture Point Control. Recently, humanoid stepping control methods that adjust footstep position and step timing have been widely used to overcome large disturbances. This is an overall working control framework with the main goal of controlling the capture point. In this presentation, I will be presenting the CPMPC and stepping controller, which are the main contributions of my research. In previous work, MPC-based stepping controllers and QP-based stepping controllers have been developed to implement stepping control. All these stepping controllers demonstrated robust balance control performance in the presence of disturbances. However, they didn't validate balance performance when there is insufficient remaining step time for step adjustment. Additionally, adjustment of the DSP time was not considered in previous research. Therefore, to address these issues, we first proposed a CP control framework based on MPC by expanding on previous MPC framework. Building on this framework, we then proposed the DSP scaling approach to enhance balancing performance for disturbances that occur when the remaining step time is not enough to adjust the step position and timing. In our first contribution, we developed the CPMPC framework by building upon the previous MPC, which had a restricted control performance due to the GMP constraint. In this framework, we introduced an additional step variable to relax the GMP constraint and improve the CP control performance. Next, the stepping controller optimizes the step timing based on the optimized footstep position from CPMPC. The step timing is adjusted to ensure that the optimized footstep position is aligned with the overall CPMPC control objective. Next, I'd like to discuss the next contribution of this work. In stepping control, the ability to adjust step position and timing depends on sufficient remaining step time to ensure its performance. However, this ability becomes gradually limited as the remaining step time decreases. Especially in many studies, step adjustments are fixed after a certain time to prevent sudden changes in the swing foot when the remaining step time is short. While using this approach is necessary, it can make balancing through stepping difficult when disturbances are applied to the robot with little remaining step time. As a result, to overcome the disturbance using stepping control, it is necessary to quickly transition to the next step. However, a fixed DSP time slows down the transition to the next step. To solve this problem, we propose a DSP time adjustment algorithm that can quickly transit to the next step reducing the DSP time. The DSP time is adjusted based on the difference between the desired and the fixed footstep position. The operation of the algorithm is based on the observation that when a disturbance is applied to the robot with little remaining step time, the desired footstep position continues to increase based on the robot's unstable state after the footstep position has been fixed. Therefore, a large difference between these two values indicates a significant disturbance at the moment, and in order to overcome the disturbance using stepping control, it is necessary to reduce the DSP time and quickly proceed to the next step. The equation for this is as follows. I will now show the simulation and experiment video. First, the simulation demonstrates the robustness of our proposed CPMPC controller against disturbances. Next, a simulation is shown with and without the DSP scaler based on proposed CPMPC. Without the DSP scaler, stepping is difficult and the robot falls over when there is little remaining step time. However, with the DSP scaler, the robot maintains balance. The first experiment demonstrates the difference in robustness between the previous and our proposed CPMPC controller. In the second experiment, the robot is subjected to a disturbance when there is little remaining step time. Only when using the DSP scaler, the robot maintains balance stably. Additional simulation and experiments can be found in the supplementary materials. I'd like to conclude by highlighting the main contributions of our work. Firstly, we proposed an MPC-based CP controller that generates the desired CMP and footstep position for the swing leg, improving the working stability. Secondly, we introduced a novel DSP adjusting algorithm to address external perturbations applied when the remaining step time is not sufficient to adjust the footstep. Thank you for listening.